All right, everybody, I'm back, and this is Brandon again, and let's just review where we're at. So I've made a basic, and by the way, I apologize for the noise. My CNC machine is running, so I put a noise gate on this that works kind of okay, but it doesn't sound great. Anyway, so we have a basic model of a single-cylinder engine, right? We did that, and right now it's basically 2 valves per cylinder and overhead cam here, right? Then I made a simulation that resulted in the ability for us to change parameters. The amount of fuel we inject, the valve sizes, the size of the piston, the size of the rod, all of that can be changed now. We can see, at least thermodynamically, what's happening, okay? So now we have to make some decisions. And I say we have to make them because we've just basically what I would call, we've gone one loop around the design spiral. We made a bunch of basic parts that are way, way far away from the end, and we've made some basic math that are still way, way far away from being confirmed and correct. But now we know enough, we have enough to kind of refine now just a bit more, and once we make these decisions, it's a lot harder to go back. It takes a lot more work to go back. So basically, let's start by talking about direct injection versus indirect injection. Most engines of today, 2025, are direct injection engines, meaning that there is an injector here that injects directly into the cylinder, into a bowl in the piston. This bowl is there so that the fuel can swirl with the air that's in this gap and properly mix. Almost all engines of today are also what's called an interference engine, meaning that when the valve goes down, if the timing belt, which connects this camshaft to the main shaft, like this, if that timing belt broke and this valve went down at the wrong time, the piston, which is moving up, would collide with it. That's called an interference engine because the valve and the piston would interfere with each other if not properly timed. So there was a time when all engines weren't this way, which brings me to indirect injection. So indirect injection looks like this. So this is how, like a IDI was configured. This is also how a Toyota HC1, which was the famous Land Cruiser diesel engine, is configured. And the way this works is your piston and your cylinder are here. And because basically what happens is as the piston compresses, the air swirls in this chamber, and then the fuel is injected in this chamber. And the reason this was done is because by injecting fuel into this chamber with only a little bit of air in this chamber, the burn starts rich, which reduces the nitrogen-based pollutants. And then as the burn travels down into the cylinder, and the cylinder then moves down as it's expanding, it slows the burn down, and so the burn becomes lean and burns up all the soot. So by doing it this way, it gave the engineers a bit of an edge to try to reduce pollutants. Now I have a graph that shows indirect injection versus direct injection, and it's undeniable that direct injection is more fuel efficient, but indirect injection, at least back when it was invented, made it easier to meet more stringent emissions requirements. And there's one more advantage of an indirect injection engine, which is that because all of the swirling happens in this pre-chamber here, you don't need the bowl here. And because you don't have the bowl, you therefore have the design freedom to put in cutouts in the piston so that your valves have room to travel down farther than they're supposed to if it should occur. If your timing belt breaks, for example, and the valves are in the wrong place when the piston comes up, it doesn't damage the valves or the piston. Huge advantage, because basically if you look at an 1.9 liter TDI from Volkswagen, which is here, you have, this is what everyone does now, but you have something that I don't like, which is a situation where you have a direct injection engine and it could collide, and it's only connected by a belt. So if the timing belt breaks, the chances are you're going to crater the whole engine. Okay, so what are the options here? Let's just say that for my engine, Brandon's favorite engine, remember, I'm not designing this for mass manufacturing for the fewest number of parts. I'm designing it based on kind of what my personal preferences would be if I was to buy a diesel engine for a truck, right, or a car. And that is, I would want direct injection because I want that efficiency, that fuel efficiency. But I also don't want a timing belt to cause the end of the engine, which brings me to getting rid of the overhead cam, which is a very simple, very cost-effective way to do everything because there's very few moving parts. It's just a cam pushing directly on valves. So how does that look? Well, it looks a lot like a 12-valve Cummins if you're familiar with it. Basically, it looks like this. In a 12-valve Cummins, you have what's called cam in block, which means the cam, like if the crankshaft was like here, you have your camshaft in the block with it right next to it. And what that means is that you have to unfortunately add all this stuff to transfer that cam motion over the cylinder and be able to actuate these valves, which is extra parts, extra cost, right? And there's just more stuff moving, more inertia of all the mass moving. So that's kind of a disadvantage, but the great thing about it is when you have the cam this close to the crank, you can just put a gear here and a gear here, and that is not a belt and it is not a chain, so it does not break. So in my opinion, I want direct injection, right? And because I want direct injection, I have to accept that it's going to be an interference engine because there's just not enough real estate on the piston to put in cutouts for the valves. And if I have to accept that it's an interference engine, I therefore would only want gears to transfer that motion from the crankshaft to the camshaft so that there's very little possibility of a failure. Now, there's one more thing. So since we're adding all of this stuff anyway, we saw from our simulations that you can, before we even started refining, we could already see that there was a lot of restriction because of the valve area. When the valves open, there's a lot of choked flow going into the cylinder, which slows down the engine, which takes efficiency from the engine. So if I'm already adding all of this extra stuff to make it reliable, I might as well go all the way. And instead of making it a 2-valve engine, I might as well just go ahead and make it a 4-valve engine. And a 4-valve engine, so if you have 2 valves, they're like this, and that leaves you very little room in the center of the piston to put your injector. And you can see that in the TDI, because what does the TDI do? The TDI not only has to put its injector at an angle to sneak it in between the valves, it actually moves its bowl over. The actual bowl in the piston is offset so that it is centered on where the injector comes out, not the center of the cylinder. So let's just get rid of all of that. I'm already adding all this extra cost and all these extra parts, so you might as well go all the way at this point, right? So if we were to, let's see how I want to show this here. Yeah, here's an example of the in-block cam if I didn't show it before. There's the rod, there's the rocker arm, and there's the cylinders. So if I'm going to go ahead and do this, I might as well just make the cylinder have 4 valves and put the injector right in the center. Not only do I get way more curtain area of each of the valves so that there's better flow for intake and exhaust, but I also now have room in the center to put the injector. So that's where I'm at. And let me just take a quick look at if I covered everything. So I've decided that going forward, I'm going to make it direct injection, not indirect. I'm going to accept that it's an interference engine, and therefore I'm going to put the cam in the block with two simple gears connecting the cam shaft to the main crankshaft. I'm going to add in a bunch of connecting rods and rockers and stuff so that I can get that cam motion up to the valves. I'm going to make it 4 valves per cylinder. I'm going to put the injector in the middle. And my last point is no turbo for now. Some of my favorite engines didn't have a turbo. And we're going to talk about this a little bit more later. But my perspective now is I'm not going to put a turbo. And then at the end, if we want to add a turbo, I'm going to make sure there's enough meat on all the components that it could tolerate boost pressure in the future if I want to add it. But, turbos are a very picky piece of machinery, and they're very picky about lubrication. And it's just, this isn't refined enough to start considering what I'm going to do about turbocharging. So I might not do it. And like I said, the 1HZ is not turbocharged. I really like that engine a lot. And you can see globally what a success that engine was. It's basically used in every war zone ever. So for now, no turbo. And so what I'm going to do is behind the scenes, I'm going to start designing all this in and modifying my single cylinder engine, putting all this in place. And when I'm done, I'm going to come back and summarize it. All right, until next time.